Gently close your eyes or allow them to rest softly upon the screen. We are about to begin a journey, not of this world, but of the countless worlds that drift in the silent, velvet darkness of space. Let your mind become a quiet vessel, ready to travel across unimaginable distances, guided only by the sound of my voice. Out there, in the cosmic ocean, are planets beyond number. They are called exoplanets, worlds that orbit stars other than our own sun. Each one is a mystery, a whispered secret of the universe. Tonight, we will drift among them, exploring the possibilities that sleep in the endless night. There is nothing to do but listen. Consider a world named 55 Cancri E. This is a super-Earth, dense and hot, where scientists believe the conditions are perfect for its surface to be composed of glittering diamond. Imagine a planet where mountains and valleys are carved from the universe's most precious gem, reflecting its star's light in a silent, dazzling display. Some alien worlds do not know the simple rhythm of a single sunrise. On planets like Kepler 16b, two suns grace the sky. Imagine a landscape bathed in the double light of a binary star system, where shadows are complex and twilight is a long, slow dance between two different stellar hues. A truly alien, yet peaceful, vista. There are planets known as hot Jupiters, gas giants that orbit impossibly close to their parent stars. Their atmospheres are scorched, their years lasting only a few Earth days. They are a testament to the sheer variety of cosmic architecture, a reminder that our own solar system is just one of many possible designs. Imagine a planet with no sun at all. These are the rogue worlds, cast out from their stellar systems to wander the interstellar darkness alone. They drift in a state of perpetual night, their only warmth coming from their own cooling core. They are the silent, solitary travelers of the galaxy. Many planets are tidally locked to their stars, presenting only one face to their sun's warmth. This creates a world of two extremes, one side in permanent, scorching daylight, and the other in an eternal, frozen night. In the terminator zone between them, a perpetual twilight could host unimaginable forms of existence. On the exoplanet HD 189733b, the weather is unlike anything on Earth. Here, the deep blue atmosphere is laced with silicate particles. Intense winds, moving at thousands of miles per hour, create a storm of horizontal, molten glass rain. A beautiful and terrifying concept, observed from the safe stillness of your rest. The term super-Earth refers to a planet more massive than our own, but not as large as a gas giant like Neptune. These worlds could have stronger gravity, deeper oceans, and thicker atmospheres. They represent a common type of planet in the galaxy, a bigger, perhaps more dynamic cousin to our own home. Let your mind drift to a world covered entirely by a single, global ocean. No continents, no shores, just an endless expanse of water that could be hundreds of miles deep. Below the surface, in the crushing pressure and absolute dark, life could exist in ways we can barely comprehend, warmed by volcanic vents. The sounds of an alien world would be profoundly different from our own. A denser atmosphere would carry sound more slowly but with greater intensity, making even a gentle breeze resonate deeply. A thin atmosphere, conversely, would make the world almost silent. Each planet possesses its own unique, unheard symphony. Time itself is relative from world to world. Consider a planet that completes a full orbit around its star in just a handful of Earth hours. Its entire year, the passing of all its seasons, flashes by in less time than a night's sleep here. A dizzying yet perfectly natural rhythm for that specific place in the cosmos. Some exoplanets may be colored in ways that defy our expectations. Instead of blue skies and green continents, imagine a world with a red sky due to the type of star it orbits. Planets on such a world, if they existed, might evolve to be black or deep purple to absorb the available light more efficiently. The pull of gravity shapes everything. On a low-gravity world, mountains could soar to impossible heights, and creatures could float through the air with delicate ease. On a high-gravity planet, life would need to be incredibly strong and low to the ground. built to withstand the constant, immense pressure. Our solar system is a delicate, stable dance. But many exoplanetary systems are far more chaotic. Imagine a system where giant planets have highly elliptical orbits, periodically swinging close to smaller worlds and disrupting their climates and stability. These are systems in a constant state of gentle cosmic rearrangement. Consider a Chthonian planet. This is the remnant core of a gas giant that has strayed too close to its star, having its entire atmosphere stripped away. What remains is a dense, hot, rocky core, a ghost of the giant it once was, silently orbiting its star in the unending vacuum. Alien life might not be based on carbon and water. Scientists speculate about life forms that could exist using silicon as a backbone, thriving in liquid methane or ethane. These beings would perceive the universe through senses we cannot imagine, on worlds we would find utterly inhospitable, but which they would call home. The night sky of an alien world could be breathtakingly different. If a planet resided inside a dense star cluster, its night would be ablaze with thousands of nearby stars, shining as brightly as our own moon. Darkness would never truly fall. Instead, a soft, multi-hued starlight would always illuminate the landscape. The concept of an eyeball planet is a fascinating one. These are tidally locked water worlds where the point directly facing the star remains liquid, forming a vast circular ocean, while the rest of the planet is frozen solid. From space, it would look like a giant unblinking eye staring into the cosmos. A planet's magnetic field is its invisible shield. A world with a very strong magnetosphere could have spectacular permanent auroras covering its entire sky. Imagine a world where the heavens are constantly filled with shimmering curtains of light, a silent, celestial light show that has no beginning and no end. Some planets may be pumice worlds, also known as superpuffs. These are planets with the size of Jupiter but with only a fraction of its mass. They have incredibly low densities, similar to cotton candy. They are so light that they challenge our understanding of how planets can even form and hold together. Imagine a planet with not one, but multiple moons. The night sky would be a slow, graceful ballet of celestial bodies of different sizes and phases. The gravitational pull from these moons would create complex and powerful tides, shaping the geology and perhaps the biology of the world below in profound ways. An iron planet is a theoretical type of world composed primarily of an iron-rich core with little or no mantle. Such a planet would be incredibly dense and small for its mass. It would be a metallic sphere, a remnant of a cosmic collision that stripped away its rocky outer layers long ago. Life on other worlds might communicate not with sound, but with light. Imagine deep-sea creatures on a dark ocean world using bioluminescence to create complex patterns, a silent language of light. Or plants on the surface that change color to signal to one another, a slow, quiet conversation across a whole forest. Consider a planet orbiting a pulsar. A pulsar is a rapidly spinning neutron star that emits beams of radiation. Life on such a world would have to withstand this intense, rhythmic pulse of energy. The sky would flash with a perfect, metronomic regularity, a cosmic clock ticking for eons. If life evolves on a rogue planet, drifting through interstellar space, it would have no concept of a sun or a star. Its entire existence would be defined by the faint geothermal heat from the planet's core and the absolute blackness of deep space. Its biology would be a masterpiece of energy conservation. The seasons on some exoplanets are extreme. A planet with a high axial tilt, much greater than Earth's, would experience radical shifts in climate. Summers could be hot enough to melt lead on one hemisphere, while the other hemisphere experiences a winter of deep, cryogenic freezing, before they slowly switch over many years. A carbon planet is a world where carbon is more abundant than oxygen. Here, the geology would be entirely different. Mountains of carbides could be eroded by rivers of oil, under a sky thick with smoggy hydrocarbons. Diamonds could be as common as rocks, forming deep within the planetary crust. The rotation of a planet defines its day. Imagine a world that rotates so slowly that its day is longer than its year. The sun would crawl across the sky with imperceptible slowness. A single period of daylight could last for months or even years, followed by an equally long and profoundly deep night. There may be worlds where the atmosphere itself is a resource. On a planet with a thick, organic, rich atmosphere, some forms of life might not need to be rooted in the ground. They could be like living zeppelins, floating perpetually in the dense air, drawing all the nutrients they need directly from the sky. On a world with two suns of different colors, say one red and one blue, the light would be extraordinary. At different times of day, the landscape would be bathed in red light, blue light, or a surreal magenta when both suns are in the sky. The very concept of color would be fundamentally different. Imagine a planet with rings as magnificent as Saturn's, but orbiting in a habitable zone. From the surface, the rings would be a permanent, breathtaking arch across the sky. They would illuminate the night, casting a soft milky glow over the landscape and making true darkness a rare and special event. The very air we breathe is unique. An alien world might have an atmosphere rich in noble gases like argon or neon. While unbreathable to us, this air could give the sky a permanent, soft color, perhaps a gentle orange or a calming violet, creating a world bathed in a perpetual, otherworldly glow. Let your mind settle on a terrestrial planet orbiting a red dwarf star. These stars are cooler and dimmer than our sun. To stay warm, the planet would need to orbit very closely, likely becoming tidally locked. The sky would be dominated by a huge, red, unmoving sun, a constant, crimson eye. Some worlds may be bombarded by cosmic debris far more than Earth. On such a planet, life might evolve to live deep underground or in the oceans to survive. The surface would be a cratered, silent testament to the violence of the cosmos, while a rich biosphere thrives in the quiet safety below. A water world might not have a solid surface at all. As you descend into its depths, the immense pressure could transform the water into exotic forms of ice, not cold, but hot and dense. A strange boundary layer of hot ice could separate the liquid ocean from the planet's rocky core. Moons can have moons. While none have been confirmed, it is theoretically possible for a large moon to capture its own smaller subsatellite. Imagine standing on a moon, watching your own tiny moonlet trace its path across the sky, with the giant parent planet looming in the background. A nested, cosmic dance. Think of a world older than Earth, perhaps billions of years older. If life arose there, it could have had an immense head start. Such a civilization, if it still existed, might be incomprehensibly advanced, their presence woven into the fabric of the planet itself, as natural as a mountain range. The shape of a planet is determined by its spin. A world that spins incredibly fast would not be a perfect sphere. It would bulge at its equator, becoming an oblate spheroid. Gravity would be noticeably weaker at the equator than at the poles, a strange and subtle property of the landscape. A lava world is a terrestrial planet that orbits so close to its star that its surface is partially or fully molten. Oceans of lava would ebb and flow, with rock vaporizing into a thin, mineral atmosphere. It is a world in a constant state of fiery creation, a planetary forge. Consider the silence of a world with no atmosphere at all, like our own moon. There is no air to carry sound, so all events are perfectly mute. Meteorite impacts, rock slides, everything happens in an absolute profound silence that is impossible to experience on Earth, a truly quiet place. A Trojan planet is a world that shares an orbit with a much larger gas giant, staying in a stable gravitational point ahead of or behind the giant. From its surface, the gas giant would be a permanent, colossal fixture in the sky, a silent, unmoving guardian in its cosmic journey. The sky of a planet in the center of our galaxy would be profoundly different. The density of stars is immense there. The Milky Way would not be a faint band, but a blinding, brilliant river of light, filling the entire sky and washing out all but the brightest of individual stars. An egg-shaped planet, like WASP-12b, is a gas giant being pulled apart by the gravity of its nearby star. Its atmosphere is being siphoned away, forming a disk of material around the star. It is a planet that is slowly and gracefully disappearing, donating its essence back to the cosmos. Life on a planet with much lower gravity than Earth could grow to enormous sizes. Trees could reach miles into the sky, and flying creatures could have wingspans like small airplanes, soaring effortlessly in the thick, gentle air. A world of peaceful, slow-moving giants. Imagine an entire ecosystem that exists not on a planet's surface, but within the clouds of a gas giant. Floating, microbial life could ride the currents and thermals, living their entire lives without ever knowing a solid ground. A biosphere suspended in the air, a world within a world. Worlds orbiting variable stars would experience a unique rhythm. The star itself would brighten and dim over days or months. The planet would be bathed in cycles of greater and lesser light and warmth, a fundamental pulse of energy that would govern the metabolism of any life that existed there. A planet with a methane cycle, like Saturn's moon Titan, would be a strange mirror of Earth. It would have rivers, lakes, and seas of liquid methane and ethane. Clouds would form and rain down liquid gas, carving channels into a landscape of frozen water ice as hard as rock. The very elements on an alien world could be different. In a much older part of the universe, planets would have formed from a cosmos with fewer heavy elements. These worlds would be fundamentally simpler, composed mostly of lighter rock, lacking the rich mineral diversity we take for granted. Let us end this first part of our journey by considering the sheer probability of it all. With hundreds of billions of galaxies, each with hundreds of billions of stars, the number of planets in the universe is beyond counting. Among them, countless worlds sleep, each with its own quiet story waiting to be told. Let us now delve deeper into the nature of ocean worlds, planets whose very identity is defined by water. Unlike Earth, where water covers 70% of the surface, these worlds are completely submerged, holding oceans that can be hundreds or even thousands of kilometers deep. In these profound depths, the pressure becomes so immense that it forces water molecules into exotic, high-pressure forms of ice, like Ice 7 or Ice X. This is not the cold, familiar ice of our world, but a hot, dense, solid layer of water, forming a strange crystalline mantle around the planet's rocky core. Life, if it exists, would be confined to the liquid layer far above, a biosphere floating between a watery sky and an alien seabed of hot ice. Now, let your thoughts drift towards the fiery giants known as hot Jupiters. These massive planets orbit their stars in a breathtakingly close embrace, completing a full year in a matter of mere Earth days. This proximity subjects them to unimaginable stellar radiation, heating their atmospheres to thousands of degrees. This extreme energy difference between their day and night sides drives winds that defy comprehension, reaching speeds of over 10,000 kilometers per hour. These are not mere winds, but supersonic flows of superheated gas that circle the entire planet, carrying heat and chemical compounds in a relentless global storm. It is a world of perpetual, violent atmospheric motion, a symphony of extreme physics playing out on a colossal scale. Let us consider the most common type of star in our galaxy, the red dwarf. These stars are small, cool, and incredibly long-lived, burning for trillions of years. Any planet in a habitable zone around such a star would need to huddle very close for warmth, likely becoming tidally locked. This creates a stable but alien environment. The Sun would hang motionless in the sky, a large, dim crimson orb. The light would be perpetually red, casting long, unmoving shadows. Photosynthesis, if it arose, would adapt to this low-energy, red-shifted light, perhaps creating forests of black or deep purple foliage. a stark and silent landscape under an eternal scarlet twilight. The search for alien life often involves looking for atmospheric biosignatures, the chemical fingerprints left by biological processes. For a planet like our own, an abundance of both oxygen and methane is a powerful indicator, as these two gases should naturally destroy each other over time. Their continued presence suggests something is actively producing both. Scientists using powerful telescopes can analyze the starlight that passes through an exoplanet's atmosphere, looking for these telltale absorption lines. It is a form of cosmic archaeology in real time, sifting through the very air of a distant world for the quietest whisper of life. A chemical echo from a world you will never see. Imagine the profound silence and solitude of a rogue planet, one that has been ejected from its parent solar system to drift forever in the blackness between the stars. Without a sun, its surface would be frozen to near absolute zero. Yet this world may not be dead. If it is large enough, the decay of radioactive elements in its core could generate enough heat to sustain a liquid water ocean far beneath a crust of ice, hundreds of kilometers thick. In this absolute, eternal darkness, warmed from below, life could emerge and evolve, completely unaware that a universe of stars even exists beyond its icy shell. The planet Kepler-10b is a fascinating example of a lava world. It is a rocky planet orbiting so close to its star that its surface temperature is believed to be higher than the melting point of iron. Instead of oceans of water, this world likely has vast oceans of molten rock. Tides raised by its parent star would cause the very surface of the planet to bulge, creating massive waves of lava that sweep across the globe. It is a world caught in a permanent fiery inferno, where the ground itself is a flowing, incandescent liquid, a vision of planetary formation that has never truly ceased. Consider a super-Earth with twice the gravity of our world. The physics of life would be fundamentally altered. Trees, if they existed, would need to be incredibly robust and likely much shorter, with dense, strong root systems to anchor them. Flying creatures would be a rarity, requiring immense power to overcome the stronger gravitational pull. Life would likely be low to the ground, built for strength and stability. Even the rain would fall with greater force. It would be a world that constantly presses down, shaping every living thing into a form of profound and patient resilience, a testament to the power of adaptation. We mentioned planets with rings, but let's imagine the view from the surface in greater detail. If you were standing on a world with a dense, icy ring system like Saturn's, the sky would be dominated by this structure. During the day, it would appear as a brilliant, shimmering arc, casting a complex, shifting pattern of shadows on the ground. At night, it would reflect the star's light, acting as a colossal moon, illuminating the landscape with a soft, ethereal glow. The night would never be truly dark. This celestial architecture would become a fundamental aspect of the world's culture, mythology, and science. There exists a class of planets known as superpuffs, which have the size of gas giants but possess incredibly low mass, some with a density so low they would float in water. The exoplanet Kepler-51d is one such world, with a density similar to that of cotton candy. Their atmospheres are thought to be enormously extended, perhaps opaque with clouds of methane haze. How these planets form and retain such vast, yet tenuous atmospheres is a deep puzzle for astronomers. They are like planetary ghosts, huge in appearance, but insubstantial in reality, challenging our models of how worlds are built. The TRAPPIST-1 system is an incredible discovery, a system of at least 7 Earth-sized rocky planets orbiting a tiny, ultra-cool dwarf star. These worlds are so close to each other that if you were standing on the surface of one, the other planets would appear in the sky not as simple points of light, but as visible disks, some as large as our own moon. The sky would be a constant, slow dance of neighboring worlds, each a potential home for life, passing by in their silent orbital ballet. It's a vision of a truly local neighborhood of planets, a family of worlds traveling together through the dark. Let's reflect on the color of alien skies. Earth's sky is blue because of how our atmosphere's nitrogen and oxygen molecules scatter the sun's light, a process called Rayleigh scattering. On a planet with a different atmospheric composition orbiting a different type of star, the sky could be a vast palette of possibilities. A thick methane atmosphere, like Titan's, creates a hazy orange sky. A thinner atmosphere around a hotter star might appear violet. The simple act of looking up would be a profoundly different experience, the world's very air painting the heavens in a unique and unfamiliar color. The concept of a carbon planet offers a truly alien geology. In an environment rich in carbon and poor in oxygen, silicon would bond with carbon instead of oxygen, forming silicon carbide. This material is incredibly hard, meaning mountains would not be made of granite, but of materials stronger than steel. Rivers would not be of water, but of liquid hydrocarbons like methane or tar. Diamonds could form so readily that entire layers of the planet's crust might be composed of them. It is a dark, durable, and bizarre world, built from a chemistry that is the inverse of our own. Imagine a world where life never reached the surface. On a planet constantly bombarded by lethal radiation from its star, or with no protective ozone layer, the land would remain sterile and barren. But deep beneath the surface of its oceans, life could thrive. Powered not by sunlight, but by chemical energy from hydrothermal vents, a complex ecosystem could evolve in total darkness and under crushing pressure. This biosphere would be completely hidden, its existence unsuspected from orbit. The planet would appear as a dead rock, while secretly harboring a vibrant and unique web of life in its abyssal depths. The age of a planet has profound implications. Earth is about 4.5 billion years old, but the universe is nearly 3 times that age. There could be planets that are 10 or 12 billion years old, formed when the universe was young and chemically different. If life arose on such a world, it has had billions of years of an evolutionary head start. The complexity and intelligence of such life is beyond our ability to conceive. The planet itself may have been transformed by this life, becoming a world-spanning living organism, a truly ancient and evolved entity drifting in the cosmic dark. Not all alien worlds are planets. Some could be moons. Moons like Jupiter's Europa or Saturn's Enceladus are considered prime candidates for life in our own solar system due to their subsurface oceans. An exomoon orbiting a giant planet in a distant star's habitable zone could be an even better candidate. It would be protected from solar flares by the giant planet's magnetic field and be tidally heated by its gravitational pull, keeping its ocean warm. From the surface of this moon, the gas giant it orbits would dominate the sky, a swirling, majestic presence that shapes every aspect of its existence. The exoplanet Proxima Centauri b is our closest known alien world, orbiting the star nearest to our Sun. It is a rocky, Earth-sized planet within its star's habitable zone. However, Proxima Centauri is a flare star, prone to violent outbursts of radiation that are hundreds of times more powerful than our Sun's. These flares would likely strip away the planet's atmosphere over time and bathe its surface in sterilizing energy. Life there would need an incredible defense mechanism, perhaps living deep underground or possessing a biology that can repair radiation damage with perfect efficiency. It is a world of both immense promise and immense peril. Consider the nature of an alien intelligence. We tend to imagine beings like ourselves, but evolution follows no predetermined path. On a world with a thick, murky atmosphere and low light, senses like sonar or electroreception might become dominant, with sight being secondary. Intelligence could arise in a collective hive mind, where the individual has little meaning, or in a slow-moving, plant-like organism whose thoughts span millennia. The very definition of self and consciousness could be fundamentally different, a product of a unique evolutionary journey on a world with its own rules and its own pressures. Let us explore the idea of a gas dwarf or mini Neptune. These are planets more massive than Earth but less massive than Neptune, and they are extremely common in the galaxy. They possess a solid rocky core surrounded by a thick, crushing atmosphere of hydrogen and helium. While not habitable on their surface, it's been theorized that at a certain altitude within their vast atmospheres, the temperature and pressure could be just right for liquid water clouds to exist. In these floating oases, suspended miles above the core, some form of microbial, airborne life could potentially arise, a biosphere held aloft in an endless sky. The rotation of a planet on its axis gives it a day-night cycle. But what if a planet had no axial tilt or obliquity? With its axis perfectly perpendicular to its orbit, it would have no seasons. The climate at any given latitude would be constant, unchanging, throughout its entire year. The poles would be in a state of permanent, frigid twilight, while the equator would experience the same perpetual, mild warmth, day after day, for millions of years. Life on such a world would evolve in a state of incredible stability and predictability, a world without the rhythmic, cyclical change that has so profoundly shaped our own. Some alien worlds might have a much higher concentration of heavy metals, like uranium and thorium in their crust. This would lead to a much higher rate of natural radioactivity. While this could be dangerous, it would also provide a constant source of geothermal energy, warming the planet from within. Life on such a world would need to be highly resistant to radiation, perhaps incorporating these heavy elements into its biology. The very ground would be a source of both peril and life-giving energy, a world glowing with its own internal, nuclear warmth, independent of its star. The end of a planet's life can be a long, slow process. As a sun-like star ages, it expands into a red giant, gradually engulfing its inner planets. For a world in this situation, the process would be a slow apocalypse over millions of years. The atmosphere would be boiled away first, followed by the oceans. The surface rock would then begin to melt, turning the planet back into the ball of lava it once was, before it is finally consumed entirely by its expanding star. It is a reminder that even worlds have lifespans, and that all things in the cosmos are part of a grand, unceasing cycle of creation and destruction. We have spoken of planets orbiting two stars, but there are systems even more complex. Consider a planet in a stable orbit within a trinary or even a quaternary star system. Its path through space would be an intricate dance, weaving between the gravitational pulls of multiple suns. The day-night cycle would be incredibly complex, with periods of multiple shadows, multiple sunrises, and perhaps no true night at all. The sky would be a clockwork of stellar motion, a celestial machine of bewildering complexity and beauty, a constant reminder of the gravitational forces that bind the cosmos together. What would alien ruins look like? If a technological civilization died out, what evidence would it leave behind? After millions of years, most structures would erode to nothing. The most lasting artifacts might be things built underground, or items left on a moon with no atmosphere to weather them. Perhaps the most durable sign would be chemical, unusual isotopic ratios in the soil, or synthetic pollutants that do not break down naturally. Future archaeologists might search for dead worlds not by looking for cities, but by analyzing the soil for the subtle, chemical ghosts of a long-vanished industrial civilization. The planet Korot 7b is so close to its star that it is tidally locked, and its dayside is a searing 2,000 degrees Celsius. This is hot enough to vaporize rock. Scientists theorize that this world may have rock rain. Rock on the dayside vaporizes, forming clouds of silicate minerals. These clouds then drift over to the cooler, permanent night side of the planet, where the vapor condenses and falls back to the surface as pebbles of solidified rock. It is a bizarre geological weather cycle where the very ground boils, becomes a cloud, and then rains back down from the sky. On a tidally locked planet around a red dwarf, the most habitable area would be the terminator zone, the twilight ring between the permanent day and night sides. Here, the temperature would be mild enough for liquid water. Life in this zone would live in a state of perpetual dawn or dusk. The red sun would hang forever on the horizon, casting incredibly long shadows across the landscape. To get more light, plants might grow to enormous heights, reaching up towards the unmoving star. It would be a world of immense, quiet forests, locked in an eternal, golden hour. Let us imagine a desert world, a planet that has lost most of its surface water, similar to Mars but in a habitable zone. With a thin atmosphere and little water vapor to trap heat, the temperature difference between day and night would be extreme. Life would need to adapt, perhaps by burrowing deep underground during the scorching day and frigid night, only to emerge at the gentle hours of dawn and dusk. The landscape would be one of wind-sculpted rock and endless dunes, a world of profound emptiness and silence, where survival depends on finding shelter from the extremes of the sky. The Great Red Spot on Jupiter is a storm that has raged for centuries. Alien worlds could have even more extreme weather phenomena. Imagine a hot Jupiter with a permanent, planet-sized vortex at the point directly facing its star, a supercyclone driven by the intense heat, or a rapidly rotating super-Earth with dozens of long-lived storms, each one larger than an Earth continent. These are not just weather patterns. They are fundamental, semi-permanent geological features of the planet, immense and complex systems of atmospheric energy that persist for millennia, shaping the world below them. A planet's magnetic field is crucial for protecting life from cosmic radiation and stellar winds. A world with a weak or non-existent magnetic field, even if it is in the habitable zone, would have its atmosphere slowly stripped away into space by its star's solar wind. Any water on the surface would be broken down into hydrogen and oxygen, with the light hydrogen escaping into space. Over eons, the world would dry out and become sterile. This invisible shield is one of the most precious and necessary features for a planet to sustain life over geological timescales, a silent guardian against the harshness of space. The star KIC 8,462,852, also known as Tabby's star, displayed a bizarre and dramatic dimming, unlike anything seen before. While natural causes are likely, it sparked speculation about alien megastructures, like a Dyson swarm, a vast constellation of orbiting solar collectors built to capture a star's energy. Though unproven, it opens the mind to the scale on which a truly advanced civilization might operate. Their engineering would not be on the scale of cities, but of entire solar systems. Their presence would be detectable not by a radio signal, but by their ability to manipulate and harness the light of their own star. The composition of an alien ocean would drastically affect the life within it. An ocean with high salinity, far saltier than Earth's, would favor life that can manage osmotic pressure perfectly. An ocean rich in ammonia or methane would require a completely different biochemistry. Imagine an ocean on a carbon planet, a deep, black, viscous sea of liquid hydrocarbons. In its oily depths, strange, non-polar life forms could exist, their cells made of lipids and waxes, their world illuminated only by the faint light filtering through a smoggy, organic sky. The possibilities for aquatic life are as vast as the chemical compositions of the planets themselves. Consider the evolution of senses on an alien world. On a gas giant's moon, constantly bathed in the intense radiation from its parent planet's magnetosphere, organisms might develop a sense of magnetoreception not just for navigation, but as a primary way to see their environment. They could perceive the invisible lines of magnetic force as clearly as we see light. On a world with a turbulent, thick atmosphere, the ability to sense minute changes in pressure could allow creatures to detect objects and movements from miles away, a form of natural, passive sonar that paints a picture of a world shrouded in fog. There is a theory that life may not have originated on Earth, but was delivered here from space, a concept known as panspermia. Hardy microbes, encased in rock, could be blasted off a planet by an asteroid impact and travel through space for millions of years before landing on another world. This means that life in a solar system, or even a galaxy, could share a common origin. We might find microbial life on Mars that is distantly related to us. Life, in this view, is not a series of independent miracles, but a single spreading phenomenon, a cosmic contagion of biology drifting on the interstellar winds. An iron planet would be the dense, metallic core of a planet whose rocky mantle was blasted away in a giant impact. Such a world would have incredibly high surface gravity and a massive magnetic field. With little geological activity like plate tectonics and no atmosphere to speak of, its surface would be a static, ancient landscape of pure metal, perhaps rusted over eons by trace elements from space. It would be a silent, heavy world, a memorial to a violent past, its story told not in canyons and craters, but in the crystalline structure of its vast metallic plains. The galactic habitable zone is a concept that expands habitability to a cosmic scale. Near the galactic center, the density of stars is high, and sterilizing supernova events are too frequent for life to get a foothold. In the far outer reaches of the galaxy, the concentration of heavy elements needed to form rocky planets is too low. The habitable zone is therefore a ring, a temperate band of stars where conditions are just right, calm enough and rich enough for complex life to form and endure for billions of years. Our Sun and Earth reside comfortably within this gentle cosmic suburb. Let us imagine a world with a permanent, global cloud cover. Sunlight would never directly strike the surface. Instead, the entire world would live in a state of bright, diffuse, shadowless light, like a perpetually overcast day. There would be no clear view of the stars, the sun, or any moons. The inhabitants of such a world might never develop astronomy, their entire concept of the cosmos limited to the luminous, featureless ceiling above them. Their universe would be an enclosed, intimate space, and the discovery of what lies beyond their sky would be a profound, paradigm-shattering revelation. The planet PSRB 1257 plus 12b is a pulsar planet, one of the first exoplanets ever discovered. It orbits a pulsar, which is the tiny, super-dense, rapidly spinning remnant of a massive star that went supernova. The planet is bathed in intense, constant radiation from the pulsar's magnetic field. This is no place for life as we know it. These planets are thought to have formed from the debris disk left over from the supernova itself, coalescing out of the ashes of their dead sun. They are second-generation worlds, born from destruction, silently orbiting the rhythmically pulsing ghost of a star. On a planet with a much thicker atmosphere than Earth's, the air pressure would be immense. Flying would be effortless, more like swimming. Even large, heavy creatures could soar on the dense air currents. The sky would be a rich, three-dimensional habitat. Conversely, the high pressure would make liquids boil at a much higher temperature. Water might remain liquid well above 100 degrees Celsius. This could allow for a form of high-temperature life to evolve, its biological chemistry adapted to a world that is simultaneously a high-pressure cooker and an aerial ocean. The Gaia hypothesis posits that life on Earth regulates the environment to make it more hospitable for itself. On an alien world, we might see this taken to an extreme. Imagine a planet where the biosphere has become so integrated with the planetary systems that it actively controls the climate. Forests might change color to absorb or reflect sunlight, and vast blooms of plankton could release gases to seed clouds, all part of a global biological thermostat. The planet would not just host life, it would be a living organism itself, a single world-spanning consciousness of perfect ecological balance. Think about the passage of time on a planet orbiting a supermassive black hole, like in the movie Interstellar. Due to gravitational time dilation, time on this world would pass much more slowly than for the rest of the universe. An hour on its surface could be years or decades elsewhere. Any life that evolved here would exist in a pocket of slow time. It would witness the universe outside its deep gravity well, aging at a fantastic rate. The stars in its sky would appear to race through their life cycles, a cosmic fast-forward playing out against the backdrop of its own slow, measured existence. Let your mind rest on the idea of silicon-based life. While carbon is more versatile, silicon is in the same group on the periodic table and can form complex molecules. Such life would be very different. It would likely exist at very high or very low temperatures where carbon-based chemistry falters. Its solvent might be liquid methane or even molten salt. It would likely be crystalline and slow-moving, with a metabolism that unfolds over centuries. It is a form of life built from rock and glass, a patient, geological intelligence born on a world hostile to the fragile water and carbon chemistry that we know. The star HD 106906b is a superjupiter on an incredibly distant and eccentric orbit, over 700 times farther from its star than Earth is from the Sun. How a planet so massive could form so far out or get thrown into such a distant orbit is a profound mystery. It is a world almost untethered from its sun, receiving negligible light or warmth. It is a lonely giant, a testament to the fact that our neat, orderly solar system is not the only model. Some systems are vast, strange, and filled with objects in orbits so extreme they challenge our fundamental understanding of planetary formation. Plate tectonics are vital for regulating Earth's long-term climate by recycling carbon. A stagnant lid planet, one without tectonic activity, would be very different. Volcanoes might be rare or non-existent, and the surface would be ancient and heavily cratered. Without the carbon cycle, the climate could run away to a permanent hothouse or icehouse state. Life on such a world would be at the mercy of its atmosphere's slow, one-way evolution, without the geological thermostat that has kept Earth stable and habitable for billions of years. It highlights the importance of the living, breathing rock beneath our feet. A planet is a theoretical type of planet that doesn't orbit a star, but orbits a black hole directly. For this to happen, it would need to be in a very specific, distant, and stable orbit. The planet would receive no light from a sun. Its only source of energy might be the faint glow from the accretion disk of matter spiraling into the black hole. The sky from this world would be a warped, gravitationally lensed view of the universe, with a central point of absolute blackness. It is a world at the edge of reality, in orbit around the most extreme object the cosmos can produce. An eyeball planet is a tidally locked world where liquid water exists in a circular patch on the day side, surrounded by a frozen shell. But there are two types. A hot eyeball is close to its star, with a sea of liquid in the center and dry, baked rock elsewhere. A cold eyeball is farther out, a world of ice where the star-facing spot melts to form a large, isolated lake. Life could arise in this lonely oasis, a circular ecosystem on an otherwise frozen world. It is a beautiful and strange solution to the problem of habitability, creating a single, precious sanctuary of life. The sounds of an alien world could be truly remarkable. On a planet with a super-dense atmosphere, like a Venusian-type world, sound would travel much faster and further. The air would be thick, like a fluid, and low-frequency sounds could propagate across the entire globe. A volcanic eruption on one side of the planet might be audible as a deep, planetary hum on the other. The world would be filled with a constant, low-frequency resonance, the sound of the planet's own geology, a deep and ceaseless vibration that would be felt as much as it is heard. Let us imagine a binary planet system, where two Earth-sized worlds orbit each other as they both orbit their star. They would be tidally locked to each other, each presenting only one face to its companion. From the surface of one, its twin would hang in the sky as a huge, unmoving celestial body, showing its own continents, oceans, and weather patterns. The two worlds could even share an atmosphere, with gases being exchanged across the space between them. Life could potentially travel from one world to the other on meteorites, creating a single, interconnected, dual-world biosphere. The James Webb Space Telescope has the power to analyze the atmospheres of rocky exoplanets in unprecedented detail. It could detect not just water vapor and methane, but complex industrial pollutants like chlorofluorocarbons, CFCs. Finding such synthetic chemicals in a planet's air would be an almost unambiguous sign of a technological, industrial civilization. It is a sobering thought. The first definitive proof of intelligent alien life might not come from a friendly radio signal, but from the unintentional detection of their pollution, a silent chemical testament to their existence, broadcast across the light years. Let's consider a planet in a globular cluster. These are ancient, densely packed spherical collections of hundreds of thousands of stars. A planet here would have a truly spectacular night sky. The heavens would be ablaze with thousands of nearby suns, making the darkness between them a deep, rich velvet instead of black. Navigation by stars would be impossible due to the sheer number. But the gravitational environment would be unstable, and the radiation from so many nearby stars could be intense. It would be a world of breathtaking beauty, but one living on a precarious, cosmic knife edge. What if life was not biological, but mechanical? This is the concept of post-biological artificial intelligence that has outlived its creators. Such beings could be self-replicating machines, traveling through space. They would not need a habitable planet, only raw materials and energy. They might inhabit the cold vacuum of interstellar space, or construct vast habitats in orbit around stars. Their intelligence would operate on timescales, and with a logic that would be utterly alien to us. The search for life might not be a search for flesh and blood, but for the complex, orderly patterns of a cosmic thinking machine. We conclude this part of our exploration by thinking about the Fermi paradox. If the universe is teeming with planets, and life is probable, then where is everybody? Perhaps civilizations are very rare. Perhaps they inevitably destroy themselves. Or perhaps the universe is not silent at all, but we simply do not have the right way to listen. They may communicate in ways we cannot detect, or they may be observing us in quiet contemplation. The silence of the universe is not necessarily an empty silence. It may be a patient silence, filled with possibilities that are simply, for now, beyond our reach and comprehension. Let us consider a newer category of potentially habitable world, the Hycean planet. This term, a blend of hydrogen and ocean, describes a planet significantly larger than Earth, covered by a deep, global ocean of liquid water, but shrouded in a thick, hydrogen-rich atmosphere. Unlike the atmospheres we are familiar with, this hydrogen envelope would create immense pressure. Yet, beneath this crush, the vast ocean could harbor conditions suitable for life. These worlds challenge our classic definitions of habitability, suggesting that life might thrive in environments far stranger and more extreme than we once thought possible, floating in the warm, dark waters under a sky made of the universe's lightest element. In the early life of a rocky planet, it is a molten sphere of chaotic, churning magma. During this phase, a crucial process called planetary differentiation occurs. Heavier elements, primarily iron and nickel, sink under their own weight towards the center, forming a dense metallic core. Lighter silicate materials, like molten rock, float upwards, eventually cooling to form the planet's mantle and crust. This is a fundamental act of organization, a gravitational sorting that establishes the planet's internal structure. This structure is not static. The hot, liquid outer core generates the planet's magnetic field, the invisible shield that will protect it for billions of years. Every world is bathed in an invisible rain of cosmic rays, high-energy particles accelerated to near light speed by distant supernovae and other violent cosmic events. On a planet with a thick atmosphere and a strong magnetic field, like Earth, most of these particles are deflected. But on a world with less protection, this constant bombardment can have profound effects. It can be a destructive force, damaging the delicate molecules of life. Yet, it can also be a creative one, inducing mutations in genetic material and thus becoming an engine of evolutionary change, driving life to adapt in new and unexpected ways. While most planets form from the primordial disk of gas and dust around a young star, some may have a more exotic origin. A helium planet is a theoretical world that could form in orbit around a white dwarf star. If the white dwarf is part of a binary system, it can pull hydrogen and helium from its companion star. This material forms an accretion disk, and over immense timescales, a new planet could coalesce from this second-hand material. The resulting world would be composed almost entirely of helium and hydrogen, lacking the heavy metal core of a typical planet. A ghostly, lightweight world born from the ashes of a stellar relationship. Within any two-body orbital system, such as a star and a large planet, there exist 5 specific points of gravitational stability known as Lagrange points. Here, the gravitational pull of the 2 large bodies precisely equals the centripetal force required for a smaller object to move with them. An object placed at one of these points will remain there in a state of perfect equilibrium. They are like quiet harbors in the gravitational currents of a solar system. It is in these stable pockets that we find Trojan asteroids in Jupiter's orbit, and it is where we place our most advanced telescopes, like the James Webb, to give them a steady, unobstructed view of the cosmos. We have discussed ocean worlds, but let us focus on their unique atmospheres. A planet completely covered in water would have an atmosphere saturated with water vapor, creating a powerful and permanent greenhouse effect. This would trap heat efficiently, keeping the entire globe in a warm, humid state with little temperature variation between the equator and the poles. The sky would likely be covered in a thick, planet-wide layer of cloud, leading to a world of diffuse, shadowless light. It would be a profoundly gentle but incredibly muggy environment, a global tropical climate, without any continents to break the monotony of the sky or the sea. On planets with extremely high atmospheric pressures and temperatures, such as the deep atmosphere of a gas giant or a very hot super-Earth, matter can exist in a state that is neither liquid nor gas. This is a supercritical fluid. Above a certain critical point of temperature and pressure, the distinction between liquid and gas disappears. The atmosphere would simply get denser and denser as you descend, with no clear surface. There would be no boiling, no condensation, just a seamless transition from a thin gas to a thick, dense fluid that has the properties of both, a truly alien state of matter where the sky slowly becomes the ocean. The concept of lithopanspermia suggests that life can travel between planets encased in rock. When a large asteroid strikes a life-bearing planet, the impact can eject rocks from the surface with enough velocity to escape the planet's gravity. If these rocks contain hardy microorganisms, they could be shielded from the vacuum and radiation of space within the rock's interior. After drifting for thousands or millions of years, this rock could then fall on another planet in the same system, seeding it with life. This process suggests that life, once it starts, may not remain confined to its home world, but can spread from one planetary shore to another. An asteroid or a small planet's orbit is not fixed forever. A subtle force known as the Yarkovsky effect can cause its orbit to change over millions of years. This effect is caused by thermal radiation. The object absorbs sunlight and then re-radiates it as heat. If the object is spinning, this emission of thermal photons acts like a minuscule, constant thruster, gently pushing the object. Depending on its direction of spin, this can cause the object to slowly spiral inwards towards its star or outwards into a more distant orbit. A quiet and patient force of celestial mechanics that reshapes solar systems over geological time. Let us journey in our minds to a stellar nursery, a vast, cold cloud of interstellar gas and dust known as a nebula. These are the places where stars are born. Within these immense, beautiful clouds, gravity slowly pulls clumps of matter together. As these clumps grow denser, their cores heat up until they become hot enough to ignite nuclear fusion, and a new star is born. The remnants of the cloud then flatten into a protoplanetary disk around the newborn star, the very same disk from which its family of planets will eventually form. These are the calm, dark, and fertile wombs of the cosmos. The Kármán line is the officially recognized boundary of space, located 100 kilometers above Earth's sea level. But for an alien world, this boundary would be in a different place. On a massive super-Earth with a thick, extended atmosphere, the edge of space might be several hundred kilometers up. On a smaller world, like Mars with a very thin atmosphere, it would be much lower. This line is not a physical wall, but the altitude at which the atmosphere becomes too thin for aeronautics to work. Each world has its own unique threshold, its own official doorstep between its sky and the great, silent vacuum beyond. We often imagine aliens as biological creatures, but one of the most profound possibilities is that advanced life becomes post-biological. A civilization could transition from fragile, organic bodies to more durable, robotic, or purely digital forms. Such beings would not be constrained by the need for water, oxygen, or a narrow temperature range. They could inhabit the vacuum of space itself, drawing energy directly from stars. Their consciousness could be vast and distributed, their thoughts operating on a timescale incomprehensible to us. The ultimate evolution of life might be to leave the planet behind and become a native citizen of the cosmos itself. A rogue wave in Earth's oceans is a rare, massive wave that is far larger than others around it. A similar phenomenon could exist in the vast rings of a planet like Saturn. The rings are composed of trillions of icy particles in a delicate orbital dance. A gravitational disturbance, perhaps from a passing moonlet, could create a density wave, a spiral pattern that propagates through the rings like a ripple in a pond. These are not waves of water, but waves of solid particles, a slow motion, majestic disturbance in the structure of the rings, a visible sign of the invisible gravitational forces at play. Let us imagine a double planet, where two worlds of similar mass orbit a common center of gravity. Like a spinning dumbbell, they would be tidally locked, each showing only one face to the other. If they were close enough to share an atmosphere, the weather would be extraordinary. A permanent, massive storm system might rage in the space between the two worlds as their atmospheres mix. Giant lightning bolts could arc from one planet's cloud tops to the others across the vacuum. It would be a system of incredible meteorological synergy and violence, a single, shared weather system spanning two entire worlds. The very chemistry of stars evolves over cosmic time. The first stars in the universe, known as population 3 stars, were forged from only hydrogen and helium. They contained no heavy elements, or metals, as astronomers call them. Therefore, these first suns could not have had rocky planets like Earth, as the necessary elements like silicon, oxygen, and iron simply did not exist yet. It was only after these first stars lived, died, and exploded as supernovae that these heavier elements were created and scattered into space, enriching the next generation of gas clouds and allowing for the eventual formation of solid, rocky worlds. The axial tilt of a planet is responsible for its seasons. Earth's tilt is a gentle 23.5 degrees, but a planet like Uranus is tilted on its side at 98 degrees. On such a world, the seasons would be extreme and last for decades. For a quarter of its long orbit, one pole would face the sun in continuous, searing daylight, while the other pole would be in a state of absolute frozen darkness. Then, as it continues its journey, the situation would slowly reverse. Life on such a world would have to be adapted to incredibly long periods of light and heat, followed by equally long periods of dark and cold. The concept of a subglacial ecosystem is one of the most promising for extraterrestrial life. On a world like Jupiter's moon Europa, a thick crust of ice may cover a global ocean of liquid water. Sunlight cannot penetrate this ice, so life cannot be photosynthetic. Instead, it would have to rely on chemical energy, likely from hydrothermal vents on the ocean floor. These vents would spew heat and nutrient-rich minerals from the moon's interior, creating a localized oasis of energy. An entire food web, a rich and complex biosphere, could exist in this perpetual darkness, completely independent of the star it orbits. The speed of a planet's rotation defines the length of its day. A very slowly rotating planet would experience extreme temperature swings between its long day and its long night. A very rapidly rotating planet would have a powerful Coriolis effect, the force that drives the swirling patterns of storms. On a rapid rotator, this effect would be so strong that the atmosphere would be organized into many narrow, straight bands of jet streams flowing parallel to the equator. Weather systems would be smaller, more numerous, and would be stretched out into long, thin ribbons, creating a striped, orderly pattern across the entire globe. Some planets may exist in systems with a high amount of interstellar dust. This dust would create a permanent haze in the solar system. a condition known as zodiacal light. From the surface of such a planet, the night sky would never be truly dark. A faint, pearly cone of light would extend from the horizon, marking the plane of the solar system. The dust would also cause more frequent and spectacular meteor showers. It would be a world where the very dust between the planets is a visible and beautiful feature of the night, a constant, gentle reminder of the material from which the world itself was born. The stability of a planetary system is not guaranteed. Gravitational resonances, where the orbital periods of two planets are a simple ratio of each other, can be a source of either stability or chaos. In a chaotic system, these resonances can amplify small perturbations over millions of years, causing a planet's orbit to become increasingly eccentric and unstable. This could lead to a planet being flung out of the system entirely, becoming a rogue planet or sent on a collision course with another planet or its star. Solar systems are not eternal clockworks. Some are delicate machines that can and do break down over cosmic time. Imagine an alien world with an atmosphere far richer in oxygen than Earth's, perhaps 30 or 40%. On such a world, fires would start much more easily and burn with incredible intensity. Lightning strikes would almost always trigger massive conflagrations. But this oxygen-rich air would also allow for more efficient metabolism. Animals could potentially grow to larger sizes, and flying creatures could be more agile and powerful. It would be a world of high energy and high risk, a place where the very air that gives life also makes the world a far more flammable and dangerous place to live. Not all stars are like our calm, stable sun. Many are flare stars, prone to sudden, violent outbursts of energy and radiation. A planet in the habitable zone of such a star would be periodically scoured by these superflares, which can be thousands of times more powerful than those from our own sun. Such an event would be catastrophic for life on the surface and could strip away a planet's atmosphere over time. For life to survive, it would need to be incredibly resilient, perhaps living deep underground or in the oceans, or possessing a rapid DNA repair mechanism to cope with the periodic blasts of deadly radiation. Let us contemplate the nature of alien thought. Human consciousness is tied to our specific brain structure and evolutionary history. An intelligent being that evolved from a herd animal might have a more collective, distributed consciousness. An intelligence that evolved from a solitary predator might lack empathy as we know it entirely. A being on a world with no night might have no concept of sleep or dreaming. We must be cautious of anthropomorphism. The minds of other living beings in the cosmos may be structured in ways so fundamentally different that communication and understanding would be the greatest of all challenges. The rings of planets are not permanent. They are transient features on a geological timescale. The tiny moonlets within the rings and the gravitational pull of larger, more distant moons constantly work to disrupt them. Particles from the rings rain down onto the planet's atmosphere, a process observed at Saturn. Over tens or hundreds of millions of years, even the most magnificent ring system will eventually erode away and disappear. We are fortunate to live in an era where Saturn's rings are at their glorious peak. A future visitor to our solar system may find Saturn as bare as the other gas giants. Thallium is a complex organic molecule that is formed when ultraviolet light or cosmic rays irradiate simple organic compounds like methane or ethane. These reddish, tar-like substances are thought to be common in the outer solar system, covering surfaces of moons like Titan and comets. It is theorized that these tholins could be a precursor to the building blocks of life. When introduced to liquid water, they can form amino acids, the very components of proteins. Comets and asteroids carrying these substances could have delivered the raw ingredients for life to the early Earth, a cosmic delivery of prebiotic chemistry. A planet's albedo is the measure of how much light it reflects. A dark planet, covered in black, photosynthesizing forests or dark oceans, would have a low albedo, absorbing more energy and becoming warmer. A bright planet, covered in ice and snow, would have a high albedo, reflecting more sunlight back into space and becoming colder. This creates a feedback loop. As a planet cools and ice forms, its albedo increases, causing it to cool even further. This delicate balance of reflectivity is a critical factor in a planet's climate, determining how much of its star's energy it holds onto. Consider a world with multiple large moons. The night sky would be a majestic, ever-changing dance of lunar phases. But the gravitational effects would be profound. The tides on such a planet would not be simple and regular like ours. They would be a complex, chaotic superposition of the pulls from each moon, resulting in unpredictable and sometimes enormous tidal bores. These powerful tides would cause rapid erosion of coastlines and could be a major driver of evolution for life in the intertidal zones, forcing creatures to adapt to a constantly and violently changing environment. The Miller-Urey experiment in the 1950s showed that complex organic molecules, including amino acids, could be formed from simple inorganic compounds under conditions simulating the early Earth. This suggests that the building blocks of life may not be a rare fluke, but an almost inevitable outcome of basic chemistry on any vaguely Earth-like world. While the leap from these building blocks to the first self-replicating organism is still a profound mystery, the evidence suggests that the universe is not barren, but is intrinsically primed to produce the necessary ingredients for life wherever conditions are even remotely suitable. What if a planet had no large moon to stabilize its axis? The gravitational tug of our moon keeps Earth's axial tilt stable over long periods. A world without such a stabilizing influence would see its axial tilt wobble chaotically over millions of years, a phenomenon known as nutation. The tilt could swing from 0 degrees, no seasons, to extreme values, causing radical and unpredictable climate shifts. The planet's polar regions could periodically point directly at its sun. Such instability would make it very difficult for complex land-based life to gain a permanent foothold, highlighting the quiet, crucial role our own moon has played in our planet's history. Let your mind drift to the end of time, to the concept of a degenerate era trillions of years from now. All stars will have burned out, leaving only cold remnants like black dwarfs, neutron stars, and black holes. The universe will be almost completely dark and cold. Yet even here, planets may persist, orbiting these stellar corpses in the profound darkness. If a civilization survived into this era, it would have to live in a universe fundamentally different from our own. A cold, dark, and incredibly slow cosmos, where the only available energy comes from the gradual decay of matter itself. A superrotation is an atmospheric phenomenon where a planet's atmosphere rotates significantly faster than the solid planet itself. Venus is a prime example, with its upper atmosphere circling the planet in just 4 Earth days, while the planet's own day is 243 Earth days long. This creates incredible winds and a uniform temperature across the planet. How this superrotation starts and is maintained is still a subject of intense study. It is a powerful reminder that a planet's atmosphere is not just a passive layer of gas, but a dynamic engine that can behave in ways completely decoupled from the world beneath it. The light from a star can exert a tiny but measurable pressure. For small particles like dust in a protoplanetary disk, this radiation pressure is a significant force. It can push smaller dust grains out of a solar system while leaving larger pebbles behind, sorting the material by size. On a larger scale, the intense light from very hot, massive stars can actually sculpt the nebulae they are born in, blowing vast bubbles in the interstellar gas and triggering new waves of star formation in the compressed edges of those bubbles. Light in the cosmos is not just for illumination. It is a physical force that shapes galaxies. Imagine a world with 2 different types of liquid on its surface, for example, water and liquid hydrocarbons, which do not mix. This could lead to a bizarre and beautiful geology. There might be oceans of water with floating continents of a lighter, oily liquid on top. Rivers of methane could flow down mountains of water ice and empty into vast, salty seas. The weather cycles would be incredibly complex, with clouds of both water and methane forming at different altitudes. It would be a world with a dual chemistry, a place where two completely different types of liquid shape the landscape in a strange and layered harmony. The faint young sun paradox notes that our sun was about 30% dimmer in its youth than it is today. Under that fainter sun, early Earth should have been a frozen ice ball, yet evidence shows there was liquid water. The solution is thought to be that Earth's early atmosphere had a much stronger greenhouse effect, rich in gases like methane and carbon dioxide, which kept the planet warm. This implies that a planet's habitability is not a static property, but a dynamic, evolving balance between stellar output and atmospheric composition, a delicate dance that must be maintained for billions of years. What would a truly alien ecosystem look like? On Earth, nearly all life is part of a food web based on photosynthesis. On a world without light, the base of the food chain might be chemoautotrophs, organisms that derive energy from chemical reactions, like metabolizing sulfur compounds from volcanic vents. The entire ecosystem would be built upon this chemical foundation. The plants of this world would be mineral-eating bacteria, and the animals would be creatures that consume them. It would be a completely self-contained biosphere, its existence powered not by the light from above, but by the heat and chemistry from below. Planetary migration is the process by which a planet can change its orbit after it has formed. Interactions with the gas and dust in the early protoplanetary disk, or gravitational encounters with other large planets, can cause a world to spiral inwards towards its star or move outwards. This is thought to be why we find hot Jupiters so close to their stars. They likely formed much farther out and migrated inwards. Our own solar system may have undergone a similar rearrangement in its distant past. Planets are not fixed in their orbits. They are cosmic travelers that can and do move home. The concept of a circumbinary planet is a world that orbits two stars at once, treating them as a single central point of gravity. From the surface of such a world, like the fictional Tatooine, there would be two suns in the sky. Sunrises and sunsets would be complex and often spectacular events, with the two suns rising and setting at different times. At times, one sun might even eclipse the other. The habitable zone around such a binary star system is more complex to calculate, but it is entirely possible for a world to exist in a stable, life-bearing orbit around two parent stars. Consider the subtle but profound influence of atmospheric pressure on biology. On a world with much lower pressure, liquids boil at a lower temperature. This would make it difficult for Earth-like life to exist, as water in its tissues might boil away. Life would have to develop pressurized bodies or different biological fluids. Conversely, on a high-pressure world, flight would be easier. But movement through the thick, soupy air would require more energy. The very density of the air an organism must breathe and move through is a fundamental parameter that would shape its entire physiology from the ground up. There are more than just rocky planets and gas giants. An ice giant like Uranus or Neptune in our own solar system is a distinct class of world. They have a small, rocky core surrounded by a vast mantle not of hydrogen and helium, but of heavier volatile compounds, or ices, such as water, ammonia, and methane. These are not frozen solid, but are compressed into a hot, dense, fluid state. Their atmospheres are primarily hydrogen and helium, but they are just the thin top layer of these strange, slushy, and deeply mysterious worlds, which may be one of the most common types of planet in the galaxy. The anthropic principle is a philosophical consideration that the universe must be compatible with the conscious life that observes it. It suggests that the fundamental constants of physics, like the strength of gravity or the charge of an electron, appear to be finely tuned for the emergence of life. If they were even slightly different, stars would not form, or carbon would not be produced, and we would not be here to wonder about it. This doesn't necessarily mean it was designed, but rather that we are the product of a universe with a very specific, and perhaps very rare, set of winning lottery numbers. Every star has a frost line or snow line. This is the distance from the star in the early solar system, beyond which it is cold enough for volatile compounds like water, ammonia, and methane to condense into solid ice grains. Inside the frost line, only rock and metal can remain solid, which is why the inner planets are small and rocky. Outside the frost line, the abundance of ice allowed planets to grow much larger, becoming the gas and ice giants. This invisible, temperature-defined boundary is one of the most important architectural features in the formation of any solar system, separating the rocky worlds from the giants. A bolide is an extremely bright meteor, especially one that explodes in the atmosphere. On a planet with a much thicker atmosphere, these events would be even more spectacular and destructive. An incoming asteroid would experience far greater friction, causing it to detonate with incredible force high in the air, creating a massive shockwave. This airburst could flatten forests and structures over thousands of square kilometers without the object ever hitting the ground. The threat from the sky on such a world would not be from impacts, but from these devastating, high-altitude atmospheric explosions. How would alien life perceive time? For a creature with a very fast metabolism, like an insect, the world appears to move in slow motion. For a being with an incredibly slow metabolism, like a form of silicon-based life, centuries might pass like moments. An intelligent species that lives for millennia would have a concept of history and the future that is profoundly different from our own. A being that reproduces by fission might have no concept of aging or generational change. Our most fundamental experience, the steady, forward flow of time, is a biological perception, and it may not be universal at all. The Roche limit is the distance from a celestial body within which a second body, held together only by its own gravity, will be torn apart by the first body's tidal forces. This is why planets have rings instead of large, solid moons very close to them. If a moon or a comet strays inside its planet's Roche limit, the gravitational pull on the near side of the object becomes significantly stronger than on the far side, stretching and ultimately disintegrating it. The resulting debris then spreads out to form a beautiful but destructive ring system, a monument to a world that got too close. Let us imagine a world without metals. In a region of the galaxy poor in heavy elements, a rocky planet could form that is composed almost entirely of silicate rocks, with no iron core. Such a planet would be unable to generate a magnetic field, leaving its atmosphere vulnerable to being stripped by its star. It would also lack the rich diversity of mineral resources that have been crucial to the development of technology on Earth. It would be a world of pure rock and stone, a geologically simpler and perhaps far less hospitable place than the metal-rich world we call our home. The Goldilocks zone is the traditional definition of a habitable zone where temperatures are just right for liquid water. But this can be expanded. A planet with a thick hydrogen atmosphere could stay warm enough for liquid water much farther from its star. A moon could be kept warm by tidal heating from its gas giant, regardless of its distance from the sun. The concept of habitability is not just a question of distance, but a complex interplay of atmosphere, geology, and orbital dynamics. Life may not be confined to the narrow, temperate band we once imagined, but could exist in many different kinds of warm pockets throughout the cosmos. A brown dwarf is an object that is too massive to be a planet, but not massive enough to ignite nuclear fusion and become a star. They are failed stars, adrift in the cosmos, glowing faintly in the infrared from the heat of their formation. It is entirely possible for planets to orbit these dim, warm objects. A world orbiting a brown dwarf would exist in a state of perpetual twilight, receiving only a dim reddish glow. Photosynthesis would be difficult, so life would likely have to rely on geothermal energy or the faint heat of the brown dwarf itself, a biosphere huddled close to a sun that never truly ignited. The interstellar medium is not a perfect vacuum. The space between the stars is filled with a tenuous mix of gas, dust, and cosmic rays. As a solar system travels through the galaxy, it moves through this medium. If it passes through a particularly dense cloud of gas and dust, this can have consequences. The dust can scour the outer planets and disrupt the orbits of comets. The influx of gas can push back the star's heliosphere, the protective bubble of solar wind, allowing more cosmic rays to penetrate the inner solar system. Even the empty space is not truly empty, and its subtle currents can affect every world within it. What if life never invented bones or shells? On a high-gravity world, a hard skeleton would be a huge advantage. But on a low-gravity ocean world, it might be an unnecessary burden. An entire ecosystem of complex, intelligent life could evolve that is entirely soft-bodied, like octopuses or jellyfish. These beings would leave almost no fossil record, their entire history disappearing with them when they die. We might look at a planet's fossil record and see nothing, concluding it was barren, when in fact, it hosted a rich and ancient civilization of beings as soft and transient as the water they lived in. We conclude this stage of our journey with the humbling realization of cosmic perspective. Every fact we have explored, every alien world we have imagined, is based on the laws of physics as we understand them from our single vantage point. There may be forms of existence, types of worlds and modes of consciousness that operate on principles we have not yet even begun to imagine. The universe is not only stranger than we imagine, it is likely stranger than we can imagine. And in that profound and endless mystery, there is a deep and calming beauty. There is always more to learn, more to discover. The universe, on its grandest scale, is not a random scattering of light. It is an intricate, ordered structure, a celestial architecture known as the cosmic web. On this immense scale, galaxies are not isolated islands, but are gathered into vast filaments and walls, stretching for hundreds of millions of light years. These luminous threads of matter are strung between dense clusters, tracing the underlying, invisible scaffolding of dark matter. In between these filaments lie the great voids, immense regions of profound emptiness. Your mind can rest in this thought that even in its unimaginable vastness, the universe is not chaos, but a place of deep and profound structure. Let us consider a Wolf-Rayet star, one of the most massive and luminous types of stars known. These are cosmic titans, nearing the end of their short, violent lives. They burn so hot and bright that they shed their outer layers in the form of powerful stellar winds, moving at millions of kilometers per hour. This process enshrouds the star in a spectacular, glowing nebula of its own making, rich in heavy elements forged in its core. Any planet orbiting such a star would be a world of extremes, bathed in intense ultraviolet light and scoured by winds of incandescent gas, a front-row seat to the beautiful and terrifying death of a giant. Our entire Milky Way galaxy, along with thousands of other nearby galaxies, is being pulled by an unseen force. This is the Great Attractor, a gravitational anomaly, located hundreds of millions of light years away. We cannot see it directly because it is obscured by the dust and stars of our own galactic plane. It is a vast concentration of mass, a cosmic river delta towards which our local group of galaxies is flowing at over 2 million kilometers per hour. It is a quiet reminder that even our galaxy is not stationary, but is on its own immense journey through the universe, pulled by a gravitational mystery we have yet to fully solve. The cosmic microwave background, or CMB, is the oldest light in the universe, a faint residual glow from the Big Bang that permeates all of space. It is a snapshot of the universe when it was only 380,000 years old, a baby picture of the cosmos. The tiny temperature fluctuations in this ancient light are the seeds from which all structure, including galaxies, stars, and planets, eventually grew. When you look at a map of the CMB, you are looking at the blueprint of everything that is and ever will be. The faint, warm echo of creation itself, a soundless hum that fills every corner of existence. Imagine a planet orbiting a magnetar. A magnetar is a type of neutron star with an incredibly powerful magnetic field, quadrillions of times stronger than Earth's. This field is so intense it can distort the shape of atoms and would be lethal to any known form of life. These objects are prone to starquakes, where the crust of the neutron star shifts, causing a colossal burst of gamma rays and X-rays. A planet here would exist in one of the most extreme environments imaginable, a world held captive by a magnetic power so vast it defies easy comprehension, a place of pure and awesome cosmic force. Dark matter is a mysterious, invisible substance that is thought to make up about 27% of the universe. It does not emit, absorb, or reflect any light, so we cannot see it directly. We only know it exists because of its gravitational effects on visible matter. It is the unseen mass that holds galaxies together, preventing them from flying apart as they spin. It is the invisible scaffolding of the cosmic web. This substance is all around us, passing through our planet and our bodies without interaction. The universe has a hidden architecture, a silent, invisible majority that provides the structure for the cosmos we see. And then there is dark energy, the most mysterious component of all, making up roughly 68% of the universe. While gravity pulls things together, dark energy seems to have the opposite effect. It is causing the expansion of the universe to accelerate. It is a repulsive force, inherent to the fabric of space-time itself, that is slowly and inexorably pushing everything apart. We do not know what it is, but we can see its effect on the most distant galaxies. The universe is not just expanding, it is speeding up, growing into an ever vaster, ever emptier space, driven by a quiet, persistent energy of which we know almost nothing. The galactic year, or cosmic year, is the time it takes for our Sun and solar system to complete one full orbit around the center of the Milky Way galaxy. This journey takes approximately 230 million Earth years. The last time our solar system was in its current position, dinosaurs were just beginning to appear on Earth. This immense, slow orbit is our own planet's grandest cycle. Throughout this journey, we pass through different regions of the galaxy, denser spiral arms, quieter interarm regions, which may have subtly influenced the history of our planet over geological time. We are all passengers on this slow celestial carousel. Imagine a planet with a significant amount of xenon in its atmosphere. Xenon is a heavy noble gas, and its presence could create unusual optical effects. Due to its high refractive index, it could bend light in strange ways, perhaps creating multiple images of the sun or distant mountains on the horizon. At night, lightning strikes in such an atmosphere would produce brilliant blue-white flashes, similar to a photographer's flashbulb. The very air of this world would be a lens, subtly distorting reality, creating a landscape that is both beautiful and perceptually elusive, a world seen through a natural, gaseous crystal. The concept of a Kardashev scale classifies hypothetical civilizations based on their energy consumption. A Type 1 civilization can harness all the energy of its home planet. A Type 2 can harness all the energy of its home star, perhaps using a Dyson sphere. A Type 3 civilization can harness the energy of its entire home galaxy. These are not descriptions of what aliens are like, but rather a quiet meditation on the physics of growth. Any civilization that continues to advance will eventually need more energy. This scale reminds us of the immense, untapped potential that lies dormant in the stars and galaxies around us. A globular cluster is a dense, spherical collection of hundreds of thousands of very old stars, all bound together by gravity. These clusters orbit in the halo of our galaxy, like ancient satellites. A planet inside one of these clusters would have a truly unique existence. The stellar density is so high that the night sky would be permanently ablaze. With thousands of stars shining as brightly as Venus or Jupiter, there would be no true darkness. However, the close proximity of stars would make stable planetary orbits difficult to maintain over the long term, a world of sublime beauty but profound gravitational instability. Let us contemplate the multiverse theory. One interpretation of quantum mechanics suggests that every quantum event creates a split in reality, resulting in an infinite number of parallel universes. In one universe, a particle goes left. In another, it goes right. This would mean that every possible outcome of every event has occurred in some universe. There are universes where the dinosaurs were never wiped out, and universes where the laws of physics are slightly different. It is a vast, humbling, and unproven idea that our entire cosmos might just be one page in an infinite library of realities. A single story, among endless possibilities. The Laniakea supercluster is the galactic supercluster that is home to our own Milky Way galaxy. It is a colossal structure containing over 100,000 galaxies and is over 500 million light-years across. The name means immeasurable heaven in Hawaiian. All the galaxies within this structure are flowing towards a common point, the Great Attractor. This is our home on the grandest of scales, our local cosmic continent. Realizing that our galaxy is just one tiny part of this immense interconnected structure provides a sense of belonging to something truly vast and magnificent, a single gravitational neighborhood in an expanding universe. An oligarchic model of planet formation suggests that in the early solar system, hundreds of planet-sized objects, or oligarchs, grew in isolation in their own orbital lanes. Over millions of years, the orbits of these worlds became unstable, leading to a period of chaotic collisions and mergers known as the giant impact stage. The solar system as we see it today is the result of this violent final assembly. The planets are the survivors, the ones that consumed their smaller rivals. Our own moon is thought to be the result of one such collision. The calm stability we now enjoy was born from a distant, chaotic, and creative past. Let us imagine the biology of a creature that lives on a tidally locked eyeball planet in the twilight ring of the Terminator Zone. With a sun that never moves, there would be no day-night cycle. The creature would have no need for a circadian rhythm, no internal clock telling it when to sleep or wake. Its entire existence would be governed by the constant, unmoving light source on the horizon. Time would not be marked by the turning of the planet, but perhaps by the slow cycles of its own metabolism, or the gradual shifting of weather patterns. It would be a life of profound steadiness, lived in an eternal sunset. The rare Earth hypothesis is a counter-argument to the idea that complex life is common. It posits that while microbial life may be widespread, the emergence of complex, intelligent life requires an incredibly long and lucky combination of circumstances. These include having a stable star, a large moon for axial stability, plate tectonics for climate regulation, a Jupiter-like planet for protection from asteroids, and a suitable position in the galaxy. It suggests that our world may not be a typical example, but a rare and precious celestial jewel, an improbable sanctuary where consciousness was given the chance to awaken. Consider a world that has undergone runaway glaciation, an event known as a snowball Earth. If enough ice forms, the planet's albedo, or reflectivity, increases, cooling the planet further and causing more ice to form. This feedback loop can result in the entire planet, from poles to equator, becoming encased in a thick shell of ice. For complex life to survive such a global deep freeze, it would have to retreat to small, isolated pockets of warmth, perhaps near volcanic vents or in the deep oceans. It is a stark reminder of how fragile a planet's climate balance can be, and how life can cling to existence in the most extreme of conditions. The ultimate fate of our universe, according to current models of dark energy, will be A, heat death, or big freeze. As the universe continues its accelerated expansion, galaxies will recede from each other until they are so far apart that they can no longer be seen. Star formation will eventually cease as all available gas is used up. The remaining stars will burn out, one by one. The universe will become a cold, dark, and empty void, filled only with degenerate stellar remnants and black holes. This will not happen for trillions upon trillions of years. It is the long, slow, and peaceful end to everything, a final return to a state of quiet equilibrium. A, prebiotic, soup, is the term for the mix of organic compounds in the early oceans of a planet from which life is thought to have emerged. This soup would have contained amino acids, nucleotides, and other building blocks formed by lightning, underwater volcanic vents, or delivered by comets. From this complex chemical environment, through processes we do not yet understand, the first self-replicating molecules arose. It was the moment chemistry became biology. This transition from inanimate matter to the first spark of life is perhaps the most profound and mysterious event to have ever occurred on our world, or any other. Let's imagine a world whose crust is rich in phosphorescent minerals. During the long day, these rocks would absorb the energy from their star's light. Then, during the night, they would release this energy as a soft, gentle, and sustained glow. The entire landscape, mountains, canyons, and plains, would be faintly self-luminous. The night would never be completely dark, but would be filled with a ghostly ethereal light from the ground itself. Life on such a world might evolve to use this faint light, developing huge, sensitive eyes to navigate a world that is always, in some small way, illuminated from within. Consider a planet orbiting a star in a very eccentric, or elliptical, orbit. Its distance from the star would vary dramatically over the course of its year. This would create seasons of unimaginable extremes. During its close approach to the star, the planet would be scorched, with its oceans potentially boiling. As it swings out to the farthest point of its orbit, it would freeze over into a ball of ice. For life to exist here, it would need a strategy for extreme hibernation, perhaps spending the long, cold winter frozen solid in the ice, only to thaw and live a rapid, accelerated life during the brief, intense summer. The interplanetary transport network, sometimes called the interplanetary superhighway, is a series of pathways through the solar system created by the complex gravitational interactions between planets. These pathways require very little energy for a spacecraft to travel along. They are not fast routes, but they are incredibly efficient. Following these invisible gravitational currents and Lagrange points allows objects to drift from one part of the solar system to another with minimal effort. The universe itself provides these quiet, hidden channels, a natural roadmap written in the elegant language of celestial mechanics, waiting to be used. What if a planet formed with no significant axial tilt? With its rotational axis perfectly upright relative to its orbit, it would have no seasons at all. The climate at any given latitude would be constant and unchanging throughout the year. The equator would experience the same weather every single day, as would the temperate zones and the poles. Life on this world would evolve in an environment of extreme predictability. There would be no seasonal migration, no hibernation, no spring bloom. The rhythm of life would be governed not by the changing year, but by the simple, monotonous, and eternal cycle of day and night. A superhabitable planet is a theoretical world that would be even better suited for the emergence and evolution of complex life than Earth. Such a world might be slightly older, larger, and warmer than Earth. It might orbit a K-type star, which is longer lived and more stable than our own Sun. It could have a slightly thicker atmosphere for better heat distribution and radiation shielding, and a shallower ocean to encourage greater biodiversity. It is a humbling thought that our home, as perfect as it seems to us, may not be the best possible environment, and that even more lush and vibrant worlds could be sleeping in the darkness. Imagine a world with a nitrogen cycle fundamentally different from ours. If a planet lacked the specific bacteria that convert atmospheric nitrogen into a usable form for life, then nitrogen, despite being abundant, would be biologically inaccessible. Life would be severely limited, starved of a crucial building block for proteins and DNA. This highlights the profound importance of the microbial world. It is the invisible work of bacteria and archaea that sustains the entire biosphere, running the great chemical cycles of the planet. Without them, even a beautiful, water-rich world could remain a sterile desert. Every star, including our Sun, emits a constant stream of charged particles known as the solar wind. This wind flows outwards, creating a massive bubble in the interstellar medium called the heliosphere. This bubble is our solar system's protective shield, deflecting the majority of high-energy cosmic rays from the galaxy beyond. The edge of this bubble, where the solar wind finally collides with the interstellar medium, is called the heliopause. It is the true, final boundary of our solar system. The Voyager probes have crossed this boundary, becoming the first man-made objects to enter the space between the stars, a quiet and lonely sea. Let us imagine a world where the dominant life forms are crystalline in nature. They would not be based on the soft, messy chemistry of carbon, but on the precise, geometric structures of minerals. Their growth would be a slow process of accretion, their thoughts a cascade of piezoelectric charges through their crystalline lattice. Their lifespan could be measured in millennia. They might not even recognize us as alive, seeing us as fleeting, chaotic blurs of disorganized matter. It is a form of life that is patient, geological, and profoundly alien. A consciousness made of living stone. The Great Silence, another name for the Fermi paradox, can be contemplated in a calming way. Perhaps the reason we hear nothing is not because no one is out there, but because the vastness of time and space makes contact extraordinarily difficult. Civilizations may rise and fall like fireflies in the night, never existing at the same time as their nearest neighbors. Or perhaps advanced civilizations have a prime directive of non-interference, choosing to watch younger worlds grow without interruption. The silence may not be an absence, but a form of respect, a quiet allowance for every world to find its own path. Consider a world whose atmosphere is opaque to visible light, but transparent to radio waves. For life on this world, the primary sense would not be sight, but a form of natural radio astronomy. They would see the universe not in terms of light, but in the radio emissions of pulsars, quasars, and distant galaxies. Their sky would be a symphony of cosmic frequencies. They would have a deep understanding of the universe's most energetic processes, while being completely unaware of the simple beauty of a star's gentle, visible glow. Their entire perception of reality would be shaped by the invisible universe. The geocorona is a faint, tenuous cloud of hydrogen gas that forms the outermost layer of Earth's atmosphere. It is so vast that it extends far beyond the orbit of the moon. This means that when we see the moon in our sky, it is technically moving through the very edge of our own atmosphere. This invisible halo is the final, ethereal whisper of our planet, a sphere of influence that stretches deep into the local space environment. It is a quiet reminder that our world's presence is larger and more subtle than we can see, a gentle, gaseous embrace around our nearest celestial neighbor. What would the archaeology of an ocean world look like? Without fire, metalworking would be nearly impossible. Without solid ground, large, permanent structures would be difficult to build. The ruins of a civilization on such a world might not be cities of stone, but perhaps vast, genetically engineered coral reefs, or beautifully carved structures on the ocean floor. Their most advanced artifacts might be complex, knotted patterns of kelp, or subtle chemical changes in the water itself. It would be a history written not in stone and steel, but in the quiet, patient, and living language of biology. Let us imagine a civilization that lives on a planet with no fossil fuels. Their technological development would follow a completely different path. Without coal or oil, their industrial revolution would have to be powered by renewable sources from the very beginning: wind, geothermal, and direct solar power. This might lead to a slower, but perhaps more sustainable technological growth. Their cities might be designed to be in perfect harmony with wind patterns and sunlight, their entire society shaped by the necessity of living in balance with the direct, daily energy income from their star. The cosmological principle is the assumption that, on the largest scales, the universe is homogeneous and isotropic. This means that it is roughly the same everywhere and looks the same in every direction. There is no special place, no center, and no edge. Our position in the cosmos is not privileged. This is a profound and humbling idea. It means the laws of physics that we observe here on Earth are the same laws that govern the most distant galaxies. It makes the universe a knowable place, a vast but orderly expanse that is open to our understanding, no matter where we are within it. Consider a world that never experienced a major asteroid impact after life began. The process of evolution might have been much slower and less dynamic. Mass extinctions, while catastrophic, often clear the way for new life forms to emerge and diversify. On a perfectly safe and stable world, the dominant species might have remained unchanged for hundreds of millions of years. reaching an evolutionary dead end. It is a strange thought that the very catastrophes that have shaped our planet's past, the moments of greatest destruction, may have also been the necessary catalysts for the complexity and intelligence we see today. The concept of a protoplanetary disk is where all of these worlds begin. It is a spinning, flattened cloud of gas and dust surrounding a newborn star. Within this disk, tiny dust grains stick together, growing into pebbles, then boulders, then planetesimals, and finally into full-fledged planets. It is a slow, patient process of construction, playing out over millions of years. Every world in our solar system, including our own, was built from this shared reservoir of primordial material. The ground beneath you is made of ancient stardust, once part of this beautiful, glowing, cosmic nursery. Let's consider the smell of space. While we cannot smell the vacuum directly, astronauts consistently report a distinct odor on their suits after a spacewalk. They describe it as being like seared steak, hot metal, or welding fumes. This smell is thought to be caused by high-energy vibrations in particles that stick to their suits, or perhaps from reactions with atomic oxygen. It is the faint, chemical scent of polycyclic aromatic hydrocarbons and other compounds that drift in the void, a subtle reminder that even the emptiness of space is filled with a complex chemistry, the raw ingredients of worlds. The bootstrap paradox is a thought experiment in which an object or piece of information has no origin. Imagine a time traveler who gets a copy of Hamlet from the future, then travels back in time and gives it to Shakespeare to copy and publish. In this loop, who actually wrote Hamlet? The information exists, but it was never created. If time travel is possible, such causal loops could exist for planets, or even life itself. It is a gentle puzzle for the mind, a question about cause and effect that bends our understanding of how things must begin, a quiet, infinite circle with no start and no end. Every 2 years, Mars enters a phase called solar conjunction, where it passes directly behind the Sun from our perspective. During this time, the Sun's immense radiation interferes with and blocks all radio communication between Earth and our robotic explorers on Mars. For a few weeks, we are completely cut off. Mission controllers must pre-program the rovers to operate autonomously and safely during this period of celestial silence. It is a forced pause in our interplanetary conversation, a humbling reminder of the immense power of our star and the delicate nature of the communication lines we have stretched across our solar system. The three-body problem in physics states that while we can perfectly predict the orbits of 2 celestial bodies, the motion of 3 or more bodies interacting gravitationally becomes chaotic and cannot be predicted in the long term. This means that the future of our own solar system, with its 8 planets and countless smaller bodies, is not perfectly knowable. While stable for now, over immense timescales of billions of years, small perturbations could grow, and the orbits of planets could change in unpredictable ways. The clockwork of the heavens is not perfect. It has a deep and inherent creativity to it, a subtle chaos that makes the distant future a mystery. Let us imagine a world where the primary solvent for life is not water, but sulfuric acid. This is not as outlandish as it sounds. The clouds of Venus are rich in sulfuric acid, and some scientists have speculated that microbial life could exist there. Life in such a medium would require a completely different biochemistry, perhaps using silicon-based polymers like silicones, which are stable in acid, instead of carbon-based proteins and DNA. It would be a form of life born from one of the most corrosive substances imaginable, a testament to the fact that biology is ultimately a question of chemistry, and the possibilities are vast. The pale blue dot is the name given to a photograph of Earth taken by the Voyager 1 spacecraft from a distance of 6 billion kilometers. In the image, our planet appears as a tiny single pixel of light, almost lost in the vastness of space and a scattered ray of sunlight. It is a profound and humbling perspective. Everything that has ever happened in human history has happened on that tiny, distant mote of dust. It is a quiet reminder of our cosmic isolation, but also of the preciousness of our world, the only home we have ever known, a tiny, fragile stage in the great cosmic arena. A stellar remnant is what is left behind after a star has exhausted its nuclear fuel. The type of remnant depends on the star's initial mass. Sun-like stars will leave behind a white dwarf, a dense, cooling core of carbon and oxygen. More massive stars will explode as supernovae, leaving behind an incredibly dense neutron star. The most massive stars of all will collapse into a black hole, an object with gravity so strong that nothing, not even light, can escape. These are the beautiful and silent ghosts of the cosmos, the final, quiet states of stellar evolution, each one a monument to the star that once was. The SETI project, the search for extraterrestrial intelligence, has been scanning the skies with radio telescopes for decades, listening for a deliberate signal from another civilization. So far, the search has been met with silence, but the act of listening itself is a profound one. It is an expression of hope, curiosity, and our deep-seated need to know if we are alone. The project continues, patiently pointing its dishes at distant stars, waiting for a signal that may never come. But in its quiet, persistent vigil, it affirms our own place as a species that has learned to look up and wonder. As our journey through these alien worlds comes to a close, let the vastness of it all bring you a sense of peace. The universe is not a place to be feared, but a place of infinite variety and endless wonder. The same physical laws that create swirling nebulae and distant galaxies are at work within your own body. You are made of the same stardust that builds these worlds. You are not separate from the cosmos, you are a part of it. You are a way for the universe to know itself. And now, it is time for this small part of the universe to rest. All the complexity, all the facts and theories can now fade into the background. Let them become a soft, gentle murmur, like the sound of a distant ocean. There is nothing more you need to learn tonight. There is nothing you need to solve. Your mind has traveled far, across unimaginable distances. And now, it is time for it to come home, to return to the quiet, safe harbor of your own deep and restful sleep. Let go of the journey, and allow yourself to drift into the peaceful darkness that awaits. The final and most wondrous alien world is the one you will soon explore. It is the world of your own dreams. It is a universe built from your own memories, hopes, and quiet thoughts. It is a place where the laws of physics are gentle and malleable. There are no equations to solve there, no distances to cross. There is only the effortless drift of consciousness. Your breathing is slow and steady. Your body is heavy and relaxed. You are on the very edge of this inner world, ready to cross the threshold into a place of deep and restorative peace. The stars will continue their silent watch, as they have for billions of years. The planets will continue their graceful orbits. The great cosmic story will continue to unfold, with or without our observation. There is a great comfort in this. The universe is vast and eternal, and your only task now is to let go. Allow yourself to become a small, quiet part of it all. Feel the gentle pull of sleep, like a quiet gravity, drawing you down into a state of perfect stillness and tranquility. Surrender to it. Your journey is complete. The ship has reached its final destination, a place of absolute calm. The engines are silent. The view outside is one of serene and endless darkness, punctuated by the faint, distant light of sleeping stars. There is nowhere else to go. There is nothing left to do. All that remains is rest. Deep, profound, and peaceful rest. Let your awareness dissolve into the quiet void. Let go and sleep. Sleep now.